Zepto delivers groceries in 10 minutes, not 10 minutes on average, 10 minutes for every single order. To pull that off, they built a 7-layer system where each piece has a strict time budget. If any one piece misses its budget, the 10-minute promise breaks. 8 minutes from now, you will understand the whole system, every layer, every connection, and be able to explain it clearly in any interview. 5 things. The 7-layer architecture, a diagram you can draw on any whiteboard in 3 minutes, the end-to-end order flow, every service call shown step by step, the 10-minute constraint and how it forces every design decision, the storage choices at each layer and why, and the interview framework for Design Zepto. Let us go. Start with the two client apps. The customer app on your phone is where you browse products, add items, and place your order. The delivery partner app on the rider's phone receives the order assignment and sends GPS location updates every 3 seconds so you can watch the dot move on your map. Both apps talk to the same backend. The customer app sends every request through the API gateway first. This is layer 3. Think of it as the security guard and traffic director. It checks your login token and enforces rate limits, then routes your request to the right service. Layer 4, the WebSocket server, is revealed on the right. It is the live connection that pushes updates to your phone. The delivery partner app also sends every request through the same API gateway. There is no separate entry point. One gateway handles all traffic from all clients. Customers placing orders and partners sending GPS updates all come through here first. The API gateway routes incoming requests to the order service, layer 5, and the brain of the system. It decides which dark store is nearest, checks if items are in stock, assigns a delivery partner, and writes the order. Every business decision happens here. The order service reads inventory from Redis. Layer 6a. Redis lives entirely in RAM. Nothing on disk. Every inventory count is stored as a simple number. Read it in under 2 milliseconds. Subtract 1 atomically when an order is placed. Anything that needs to be fast lives here. Confirmed orders are written to PostgreSQL layer 6b. This is the permanent database. Every order, every user account, every product is stored here. PostgreSQL is AC compliant. Every write either fully succeeds or fully rolls back. No partial saves. Layer 7 S3 and CDN stores product images at the edge so they load fast without hitting this database. After writing the order service notifies the WebSocket server, layer 4. The WebSocket server holds open, persistent connections to every active customer and delivery partner simultaneously. It is the real-time relay between the backend and the mobile apps. The WebSocket server pushes order confirmed directly to your phone. No polling, no refresh, no button press. The update arrives because the server pushed it over the persistent connection that was open before you even tapped place order. At the same moment, the WebSocket server pushes a different message to the delivery partner's phone. New order 0.8 kilometers away. Both pushes happen simultaneously. The partner sees the pickup address. The 10-minute clock is already running. Here is why this architecture looks the way it does. The 10-minute delivery promise forces a time budget on every single layer. Inventory check must finish in under 5 milliseconds. That rules out a database query, which takes 20 milliseconds. So inventory must live in Redis dark store assignment must finish in under 50 milliseconds. That rules out scanning 400 stores with distance calculations. So geohash lookup in Redis is used instead. Every design choice you see flows from this constraint. You tap place order. Your app sends an HTTPS post request, a standard web request to the API gateway. The gateway does two things instantly. It checks your login token to confirm you're a real user, and it checks your request count to stop bots. If both checks pass, the request moves forward. The API gateway passes the request to the order service. The order service is stateless. It does not remember anything between requests. Every time it needs data, it reads from Redis or PostgreSQL. Every time it needs to save something, it writes to PostgreSQL. Stateless design means any of the 50 order service servers can handle any request, no stickiness needed. The order service checks if your items are in stock. It sends one command to Redis, ageGetA, which means get this value by key. The key is inventory colon store ID colon product ID. Redis finds this in memory and replies in under 5 milliseconds, faster than a single blink. If stock is above 0, it atomically subtracts 1. Atomic means no two orders can grab the same last unit at the same instant. With stock confirmed, the order service writes the order to PostgreSQL, the permanent database. It records the order ID, your items, your address, and the assigned dark store. The dark store is found using a geohash lookup. Your location is encoded as a short string and matched to the nearest store prefix in under 2 milliseconds. The entire write takes under 50 milliseconds. The order service now tells the WebSocket server that a new order exists. The WebSocket server holds open connections to both your phone and the delivery partner's phone simultaneously. It pushes two notifications in parallel. Your app gets order confirmed and the nearest available partner gets new order 0.8 kilometers away. Both arrive in under 1 second. Your phone receives the order confirmed message over the persistent WebSocket connection. No polling, no refresh, no button press. The server pushed it to you. The 10-minute countdown starts on your screen. At the same moment, the WebSocket server pushes a different message to the nearest available delivery partner's phone. New order 0.8 kilometers away. The partner sees the pickup address and accepts. Both pushes yours and the partners happen within the same second. Finally, the API gateway returns the HTTP 200 OK response to your app, the synchronous reply to your original post request. Your app receives this confirmation. All 8 hops are now complete. The entire flow from tapping place order to seeing order confirmed takes under 1 second. The 10-minute clock is running. Redis is the fast whiteboard. It lives entirely in RAM. Nothing goes to disk during a read. Every inventory count is stored as a simple number under a key, like inventory store 123 SKU 456. You read it in under 2 milliseconds. You subtract 1 atomically. You store session tokens. You store order state. Anything that needs to be fast goes here. Redis is why Zepto can check stock in 5 milliseconds instead of 20. PostgreSQL is the permanent record. It stores orders, user accounts, product catalog, and pricing. It is relational, meaning you can join tables, and ACID ID compliant, meaning every write either fully succeeds or fully rolls back. When a product is not in Redis cache, a cache miss, the order service falls through to PostgreSQL, reads the data, and writes it back to Redis for the next request. Redis hit rate must stay above 99% or the database overloads. S3 and CDN handle images. When you browse Zepto and see product photos loading in under 50 milliseconds, those images are not coming from the database. They are served from a CDN edge server geographically close to you. S3 stores the original images. The CDN caches them at edge nodes worldwide. The URL for each image is stored in PostgreSQL. Images have a 30-day cache TTL. They change rarely, so they stay cached for a long time. Hop 1. You tap Place Order. Your phone sends a post request, a standard web request to the API gateway. The API gateway is the single entry point for every request in the system. It immediately checks two things: your login token to confirm you're a real user and your request count to block bots. If both pass, the request moves forward. Hop 2. The API gateway routes the request to the order service, the brain of the system. The order service is stateless, meaning it does not store anything in memory between requests. Every time it needs data, it reads from a database. Every time it needs to save something, it writes to a database. Stateless design means any of the 50 order service servers can handle any request. No sticky routing needed. Hop 3. The order service checks if your items are in stock. It sends one command to Redis, hget, which means get this value by key. Redis is an in-memory database. Everything lives in RAM, nothing on disk. It answers in under 5 milliseconds, faster than a single blink. If stock is above 0, it atomically subtracts 1, so no two orders can grab the same last unit. Hop 4. With stock confirmed, the order service writes the order to PostgreSQL, the permanent database. It records the order ID, your items, your address, the assigned dark store, and the delivery partner. PostgreSQL is A-side compliant. Every write either fully succeeds or fully rolls back. No partial saves. The write completes in under 50 milliseconds. Hop 5. Order confirmed and saved. The order service tells the WebSocket server that a new order exists. The WebSocket server is a real-time relay. It holds open persistent connections to both your phone and the delivery partner's phone simultaneously. Think of it as a live phone line that stays open the entire time your order is active. Hop 6. The WebSocket server pushes order confirmed to your phone over the persistent connection. No polling, no refresh, no button press. The server pushed it directly to you. Your app receives it and starts the 10-minute countdown timer. This is the moment the order is locked in from your perspective. Hop 7. Simultaneously, the WebSocket server pushes a different notification to the nearest available delivery partner's phone. New order zero point 0.8 kilometers away. The partner sees the pickup address and item count. Both notifications, yours and the partner's, arrive within 1 second of when you tap place order. Hop 8. The API gateway returns the HTTP 200 OK response to your phone, the synchronous reply to your original post request. Your app receives this confirmation alongside the WebSocket push. All 8 hops completed. Every component stayed within its latency budget. The 10-minute clock is running. That is the complete Zepto architecture. 7 layers, 8 hops, one 10-minute promise. 5 phases for the interview. First, nail requirements, 10-minute SLA, real-time tracking, inventory accuracy. Second, estimate scale, 10 million orders per day, 100,000 concurrent WebSocket connections. Third, draw the 7 layers and walk through one order end to end. Fourth, go deep on the interviewer's chosen topic. Inventory caching, WebSocket scaling, or dark store assignment are the most common. Fifth, address trade-offs. Always acknowledge the tension between consistency and latency for inventory counts. This framework works for Zepto, Blinkit, Swiggy, Instamart, and any quick commerce system. 7 layers, 3 storage systems, Redis for speed, PostgreSQL for permanence, CDN for images, one 10-minute constraint that drives every design decision. 8 hops from place order to order confirmed. You can now draw this on a whiteboard in 3 minutes and explain every component's purpose. Next video, real-time order tracking. After you place an order, Zepto pushes the delivery partner's GPS location to your phone every 3 seconds. How does that work without you refreshing? WebSocket upgrade handshake, dual client architecture, order channel routing, all in 8 minutes. Subscribe to ByteLearn for one Zepto system design concept per week. Under 8 minutes, interview ready. Hit the bell. See you Thursday.